These little bottles aren't taking up too much space, but I'm a little suspicious about the one on the far left. We'll talk about why in a moment, but everything else here should be okay, and I'd like to see if the ferroin is in good shape for a later reaction. Let's see what we've got. Besides ferroin, there are 4 single constituent solutions. There shouldn't be any shelf stability problems among them. Here's the ferroin. It's an oxidation reduction indicator, which means if it happens to be in a reducing environment, it will be red. If it's in an oxidizing environment, it will be blue. The phenanthroline binds to the iron atoms and gives a strongly colored complex. When the iron 2 is oxidized to iron 3, the color of the complex goes from red to blue. This effect is pronounced in the first demonstration. This model shows that phenanthroline is a bidentate ligand and that there are 3 moles of phenanthroline for every mole of iron. It also shows the really cool propeller shape of the complex. And if you look really close, you can see the reason for my concern. This ferroin expired in 2013. Now, I usually scoff at chemical expiration dates, but when the chemical's function is sensitive to oxidation, I get a little bit more serious about the date. Here we go. In a 50 milliliter beaker, we'll combine the reagents. First, we have 6 milliliters of the 0.5 molar potassium bromate solution. Then, in goes 2.5 milliliters of the 0.5 molar malonic acid solution. Followed by 1 milliliter of 0.5 molar potassium bromide. As you can see, this addition produces an amber color. When I add the 0.6 milliliters of 6 molar sulfuric acid, you'll see that amber color darken. That's elemental bromine, so be sure to have good ventilation at this stage. I'll swirl this mixture periodically, and in a few minutes the amber color will fade and then disappear altogether. Here's how I think this could have gone better. This is a variation of a classic reaction named for the 2 people who contributed the most to its study. The originator, Boris Belousov, and a graduate student, Anatol Zhabotinsky. Since Russian names tend to intimidate non-Slavic people, this class of reactions is referred to as BZ reactions in the West. In another variation I'll be doing in this video, the malonic acid alone is used to evolve the bromine, and the stronger sulfuric acid is added later, once the initial bromine evolution has faded. Here, there was a clear amber color upon addition of the malonic acid, and I think it would have been best to wait for it to fade before adding the sulfuric acid. These reactions, which were studied in the 1950s and 1960s in the Soviet Union, were unknown to Western science until 1968. They are unique in that the products to a reaction become the reactants for another reaction, and they cycle between the different reactions. The concept of equilibrium is challenged by these reactions because they're so chaotic. Eventually they do stabilize and reach something like equilibrium. The common thread between the large variety of BZ reactions is an acid, typically malonic, and bromine, typically using bromate as a source. The catalysts are usually cerium or manganese based, but varieties exist using iron, ruthenium, cobalt, copper, chromium, silver, nickel, and osmium. It's an interesting bit of chemical history, and I encourage you to read up on it if you're interested in that sort of thing. So by now, you can see that the bromine is just about gone, and we can move on to the next step very shortly. It seems as though the reaction that produces the bromine goes pretty strong for a while, and then all of a sudden it just stops and the bromine disappears very quickly, as you can see. Let's move on now. Okay, how about now? The next step is to add the ferroin. In this case, 1 milliliter. Right away we can see a series of nice color changes. I suspect the dark color is a mixture of the oxidized and reduced forms of the ferroin, while the maroonish red and bright blue we saw only briefly are where the majority of the ferroin is either reduced or oxidized. In order to see why this variant is interesting, it's best to have the reaction mixture in a shallow layer. Now, in a perfect world, it will start propagating red and blue waves throughout the dish. But it's not a perfect world, and I picked this very moment to be impatient. It does take a few minutes for the color changes to happen, but I shut the camera off after a minute and a half, started working on preparing the next reaction, only to come back and find this. The reaction started after all. I just needed to be a little bit more patient. Let's get a better view of this, shall we? This isn't a particularly fast reaction, so I've sped this up about 4 times normal. Nile Red produced an outstanding video on this reaction not too long ago, and I'd encourage you to watch that if you want a more thorough description of the chemical reactions that are going on here. I left a link in the description. I won't repeat his work, but there are something like 9 different reactions going on in this little petri dish right now. What changes over time is which reaction or reactions are predominant at any given moment at any of the sites from which the waves are propagating. Because this is a random, chaotic process, every time this reaction is done, a different pattern will emerge. You can watch this in real time and still see the reaction happening, albeit very slowly. It's a little more exciting than watching grass grow, but it still requires some patience, which I've already admitted to be lacking. Anyway, one of the reactions that tends to predominate towards the end of the cycle produces carbon dioxide, and little bubbles start forming in the reaction mixture. It's possible to agitate the dish and start over after it turns mostly blue, which remember is the ferroin in its oxidized iron 3 form. Subsequent reaction cycles tend to degrade, and the first cycle is usually the most visually appealing. Since again, I'm only testing out the solutions, I'm going to cut it off here. I'm satisfied the ferroin is in good enough shape for use in another BZ variant. For now though, I'd like to step away from BZ for a while and talk about Briggs and Roscher. This is another reaction that has many variants, but in this one I'll be using 3 solutions. Here's what they contain. The first 2 are pretty simple, and the starch solution will require boiling, either on a hot plate or in the microwave. I'm slightly concerned about the peroxide concentration. I'm relatively certain solution C is garbage, and there's a little something curious about the potassium iodate. In the last video, we established that potassium iodate does survive long-term storage, but this potassium iodate has been acidified. In theory, that shouldn't really do much, but when I pick up the bottle and move it around, something has crystallized out. If it was the potassium iodate, will the solution still be concentrated enough to work? We'll see. Here's the lineup. Take note that everything is colorless to start with. I have this large beaker on a stirring motor, and I'll be adding 100 milliliters of each solution in the order they were listed on the slide. First was the peroxide. Next up, we'll have the potassium iodate solution. And then finally, the malonic acid and starch. There is a color change, so that's a promising sight. And the reaction does oscillate, but there's no blue starch-iodine complex. It's not too crazy to think that the starch has been thoroughly hydrolyzed sitting in malonic acid for a few years. So I have already started preparing the new solution, but at this point I hadn't finished it yet. I decided to do a little test with just adding a little bit of plain starch solution to the old malonic acid because I wanted to see what would happen. I'm using a smaller beaker because I only want to do a small test. I'll be using the same reagents I just did, 20 milliliters of the first two and about 17 or so of the last one. To that, I'll top it up to 20 milliliters with a freshly prepared starch solution of some random concentration. The concentration doesn't really matter, it's only used as an indicator in this situation. We can see right away that we do get the oscillations and the blue color, so I'll proceed with the new starch malonic acid solution and see how it does at the 100 milliliter scale. So I'm still using the other two reagents from the shelf, and in fact this 100 milliliters of peroxide emptied out that bottle. I'm not really getting much off the shelf otherwise today, so I'm happy about that at least. This is also still the potassium iodate solution with the crystals in it. The only thing new is the starch malonic acid solution, which also contains some manganese sulfate, which acts as a catalyst in this reaction. We can see right away the blue is much bluer. And that colored vortex was pretty spectacular. I'll adjust the stirring a little bit here. We can also see that the gas evolution is a bit more pronounced than in the previous runs. That's probably the malonic acid going to carbon dioxide again, which has me wondering if the malonic acid decomposes in solution too. Although the gas might also be oxygen from the peroxide decomposing. I'm not too sure, but someday I plan to make a study of this reaction's variants along with some more variants of the BZ reaction. As I mentioned briefly, this is the Briggs-Roscher reaction, and there are dozens of variants to this one too. The original was essentially the same, but they used concentrations that were much lower and dilute perchloric acid as an additional oxidizer. With the lower concentrations, they were able to record some 40 oscillations in just 8 minutes. Some other variants include using various ketones instead of malonic acid, and using fluorescent dyes instead of starch, which, by the way, could be more than just an indicator after all. Since there are very few known oscillating reactions, the BZ and Briggs-Roscher reactions get a lot of attention. As the reaction progresses, the oscillation frequency decreases, and by the end of it, the blue color gets darker and darker, and the smell of iodine becomes stronger and stronger. I still have 2 more variants of the BZ reaction I'd like to test, so I'm going to make a part 2 of the oscillating reactions. They really are quite fascinating, and I hope you enjoyed seeing them in action as much as I did. Thanks a lot for watching, and I'll see you next time.